So I want to introduce a problem to you, and that's going to lead us to a solution method called completing the square. So in ancient times, a mathematician named, got the eraser on, sorry, named Al-Khwarizmi, I hope I spell this correctly, something pretty close to that, Al-Khwarizmi, uh, used the newly created symbols of algebra to solve a problem that was really, really difficult. And so for them, because they didn't really have algebra yet, all they had was geometry and arithmetic. And so the new symbols of algebra were just being invented. And the problem goes something like this. Suppose you want to build a room and on a piece of land, and you know that this building you're going to build on this piece of land is a rectangle. Okay? Now, you know that the area of that rectangle is equal to 39 meters squared. Okay? And then what you want to do is you want to make a room and two rooms in your building, and these rooms have to conform to certain measurements. So one of the rooms is a square. Now, we do not know the lengths of the sides of the square. We just know that it's a square. The other room from the rectangle, we know that this side is going to be 10 meters, like that. And so we can see that we have one room that is, the area is x squared, x times x, and the area of the second room is 10x. And when you add those together, you get 39 meters squared. So that is your, sorry about that, that is your problem statement. Now, as you can see, Al-Khwarizmi and his friends had essentially created a quadratic equation, but they did not have the quadratic formula yet, and they did not know how to solve this problem. So what they did is they tried to get clever and use a bit of geometry to help them. And what they did is this. He divided his rectangle room in two so that he had two 5 by x rooms. And so now this problem becomes x squared plus 5x plus 5x equals 39. Or in our language of today, it would be x squared plus 2 times 5x equals 39. So we're going to leave it there for a moment for the equation part, and we're going to look at the geometry. So what he did at this point is he said, maybe I can rearrange these shapes. And so that's what happened. So we take our original x by x rectangle, or square, excuse me, and then we put one of the 5 by x, let me do that in blue, one of the 5 by x rectangles down there, and we leave the other 5 by x rectangle up here. And then he noticed right away geometrically that all you have to do is that this is a square. This is a side 5 plus x. This is a side 5 plus x. So if you add this little square, which is 5 times 5, into this diagram, you end up with a perfect square. You complete the square. Pretty cool, right? Just using geometry. So then with their symbols in algebra, they were able to say, hey, what if this is x squared plus 2 times 5x plus 5 times 5, which is 25, equals 39 plus 25, which then gives us x squared plus 10x plus 25 equals 64. And using our factoring techniques, I apologize for that little pause. I had to eat a little apple crumb dessert. Anyway, now we're back. And the last thing I said was we would factor, and we could see what the factors are from the square. And so even Al-Khwarizmi could, because they didn't really know factoring yet. They just had the symbols for algebra, so they could rewrite it as x plus 5 squared equals 64. And they knew square roots from arithmetic. So then that would give them x plus 5 is equal to 8. Now, and then that would lead to x equals 3. Now, why is it just x plus 5 equals 8 and not x plus 5 equals plus or minus 8? Because we're talking about a room here, and geometrically, measurements have to be positive. Okay? Then solving for x, we would get x equals 3. So our original room would be 3 meters by 3 meters, about 10 feet by 10 feet. And the remaining room would then be 3 meters by 10 meters, or about 10 feet by 30 feet. Okay? And that's how Al-Khwarizmi took an ancient problem that was very hard to solve, and using symbols of algebra, essentially the x, was able to geometrically deduce that the correct size of the square room would be 3 meters by 3 meters. Now, I just want to mention before I go on that I'm not clever enough to go find this historically myself. Well, I am, but I didn't. I actually got this from a website called intomath.org. I had seen this demonstration before, and so I went looking for it, and that's where I found it. So I want to give them credit. Okay, let's move on. And what we want to do is we want to analyze this process now. So what happens algebraically is we want to move away from geometry, even though the geometry is cool, and we want to move towards an algebraic procedure that is repeatable. And we call that algebraic procedure completing the square, okay? Even though we're not gonna look at it geometrically, okay? Now, if we are looking at this really, really closely, one of the things I want you to know is the 10x was split up into 2 pieces. That's when we divided the room in half, okay? That's really important. We have to divide the room in half, or divide the x term in half. The next thing then that we do is we have to complete the square. So where we figure out that we end up adding 5 squared. Now, where did that 5 come from? Well, it came from this half. when we divided the 10x in half, we took that number and squared it, and we ended up adding it to both sides of our equation. So that's a procedure. And then once we did that, we just went forward, looked for the perfect square factors, and then took the square root of both sides and solved the problem. Okay? So now we're going to do this general algebraic procedure with a couple of examples. So just so you know, I'm going to make a couple of examples that are not nice at this point. All right? And I'm doing that on purpose so that you can see the process for completing the square. Okay? So here's our first example. Suppose we're doing the whole same thing. We want to do a room, and for some reason the room is 2 meters or 2 football fields long or whatever. Okay? Whatever the measurements are, it doesn't really matter. Algebra is abstract. And so what we want to do is we want to divide the number 7 in half. That's dividing the room in half. So the way we look at this is we take the 7 and we divide it by 2. That is 7 halves. Just leave it as a fraction. And then what we do? Then we completed the square. We squared this number and added it to both sides. So that number is 49/4. And so in order to complete the square here, we're going to need to add 49/4 to both sides. Now, as you can see, our problem's a little more difficult than Al-Khwarizmi's because we have fractions we have to add. That makes the factoring a little tougher. But if you'll remember, the square sides were always x plus whatever half of the 7 was. And so I know that this will factor to x plus 7 halves times x plus 7 halves, or x plus 7 halves squared. So that's the easy part of completing the square. The right side of the equation. Then now we have to add fractions. 2 is actually 8/4. So 49 plus 8 is 57/4. And now we take the square root of both sides. So we get x plus 7 halves is equal to plus or minus the square root of 57/4. Now, why do I have to put the minus here where I didn't before? Well, Al-Khwarizmi was doing a problem for a real room. We're not. We're doing this in the abstract. So we need to include both the positive and the negative square root when we take the square root of both sides. In a more advanced pre-calculus way of thinking, let me put this on the side. The square root of anything with a variable squared is actually equal to the absolute value of the variable. So when we take the square root of this quantity squared, it's the absolute value of x plus 7 halves equals the square root of 57/4, because absolute value is always a positive number. But then you have to solve the absolute value equation, which is x plus 7 halves equals the square root of 57/4, and x plus 7 halves equals negative square root of 57/4. If you remember that from Algebra 2. And that's why we always do plus or minus when we're taking the square root of both sides. It's because of definitions. Don't you love mathematics when you really learn how things fit together? All right, so let's continue on with this. At this point, we would finish this problem by subtracting 7 halves from both sides. So x equals negative 7 halves plus or minus the square root of 57/4. Okay? And if you wish, the square root of 4 is 2, so it's negative 7 halves plus or minus the square root of 57 all over 2. Since these have a common denominator, it's negative 7 plus or minus square root of 57 all over 2. And so there's our first example. I want to do one more example. All right, so let's go to the next page. And what if we had something like this? What if we had 2x squared plus 3x equals let's keep it in the room. So it could be a negative number, it'd be fine, but let's let it equal 3. We're going to keep it positive right now. Now, how does this change Al-Khwarizmi's problem? Well, how it changes it is what's happening is he has 2 rooms that are x by x, right? 2x squared. And then he has a specific length of 3 meters here, okay? Now the problem is you can't complete the square on that the way that looks. What you have to do is say, how do I turn 2 rooms into 1 room? Well, the way you do that is you divide them. And so you say, let's just look at the 1 room that's x by x, all right? And in order to do that, what we do is we divide everything by 2, or we multiply by 1/2. And so this was also discovered that in completing the square, you would have to always complete the square when the coefficient was 1x squared. At this point, we can go on and do our same procedure. We take the 3/2 and we divide it by 2, i.e. multiply by 1/2, so we get 3/4, and then we take the 3/4 and we square it to get 9/16. That's what we add to complete the square. So x squared plus 3/2 x plus 9/16 equals 3/2 plus 9/16. All right. Again, this will factor x plus 3/4, always whatever half of that coefficient is. All right. And the other side will add it together. So this will be 24 over 16. So 24 plus 9 is 33/16. Okay. And then we take the square root of both sides, so we get x plus 3/4 equals plus or minus the square root of 33/16, which gives us x equals negative 3/4 plus or minus the square root of 33 over 4. They have a common denominator, so negative 3 plus or minus square root of 33 over 4. And there you have it. How do you complete the square in a couple of examples? So really quickly, I think every student in pre-calculus should know this next thing. Somebody, after algebra is going along and doing really well, somebody goes, hey, why don't I just complete the square for the quadratic equation in that form, the general quadratic? And so when we do that, we get ax squared plus bx equals negative c. And then we divide everything by a, or multiply by 1 over a. So we get x squared plus b over a x equals minus c over a. And then, like we did before, we take b over a, multiply it by 1/2, which is b over 2a, and then square it. So we get b squared over 4a squared. And you might be thinking, I know what's going to happen here. You get x squared plus b over ax plus b squared over 4a squared equals negative c over a plus b squared over 4a squared. Factoring this, you get x plus b over 2a squared is equal to, finding a common denominator, you get negative 4ac plus b squared all over 4a squared. And you can check that on your own. You'll take the square root of both sides. So x plus b over 2a equals plus or minus the square root, and we'll put it in the more familiar form, b squared minus 4ac over 4a squared. And then we're going to subtract that, x equals minus b over 2a plus or minus the square root of b squared minus 4ac, and the square root of 4a squared is 2a. And so they have a common denominator, so we can write those together as x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And this, my friends, is the quadratic formula. And the quadratic formula comes from completing the square. In fact, if you want to think a little like Al-Khwarizmi, you could probably draw a geometric representation of this. All right? Now, that is how you do completing the square in all cases. That there's an example of each type. Here's the quadratic formula, so you can check to see if you completed the square correctly. Some errors that students make are occur in this spot when they have to simplify the radical and simplify the fraction to match answers in the back of the book. But that's really algebra, okay? Now, why would we even complete the square? And this is what I mentioned in the main video, when completing this, we have the quadratic formula. I've now completed the square for once and for all time. Why do I need to do it? Because it turns out there are problems we are going to see later. And the problems we're going to see later have to do with something called conic sections. And that's sort of the analytic geometry part of pre-calculus. Another place you see completing the square is much, much later when you look at three-dimensional shapes that are generalizations of the conic sections, like paraboloids or ellipsoids or hyperbolic paraboloids, etc. And it turns out completing the square becomes a way to simplify things that are quadratic in form. In other words, they're basically an x squared equation. Okay? And so, knowing how to complete the square is a way you can simplify work that you're doing. So, this is your bonus video. Good luck and enjoy it. I'm sorry it's a little bit long, but it just as one thing, you have to teach it as one thing. So I had to separate it out. And I'm sorry it's not in there for 1.02, but I'll stick it between the lessons as a bonus video. Alrighty? Anyway, here we go. I'm going to save. Bye-bye.